Hello everyone, this is Ying. I'm a thermal engineer from Facebook. Today, Albert and I will talk about the standalone rack-level liquid cooling solution design. As a first portion, I will cover the thermal architecture design, and Albert will talk about the detailed design, also walk you through some preliminary testing data. So a standalone rack-level liquid cooling system has some advantages. For example, it requires no facility change. The key components are compatible for OpenRack v3. It has a high serviceability and independent rack-level cooling control. So at the thermal architecture level, it is an air-assisted liquid cooling system, which means the heat dissipated from the high-power components, such as from the CPU and the GPU, is transferred to the rear-door heat exchanger through cold plate, and the other heat from the IT gears is cooled by the air directly. Regarding to the heat dissipation path at the coolant side, the coolant going through the cold plate in each of the chassis carries the hot heat from the major heat components such as CPU and GPU, and then it's going through the rear-door heat exchanger, reduce the temperature, and pumped through the coolant distribution unit and back to the cold plate, and the cycle continues. So at the air side, the cold air from the DC going through the rack or each of the chassis, and it's carried some of the heat from the other components, which is cooled by the air directly, and then the preheated air going through the rear-door heat exchanger to cool the coolant and become even warmer, then exhausted to the hot air side of the data center. So the total CFM going through the rear-door heat exchanger actually is controlled by the rack level, which is based on the CFM per watt requirement. So for the next portion, I will hand over to Albert, and he will talk about the detailed design. Thanks, everyone.
This is Albert from Win Thermal Solution Team. About today's topic, I would like to introduce the rack-level liquid cooling solution. The design concept is similar with the assistant liquid cooling. I want to spend a little time to explain here what it means standalone. In this solution, it means first, the solution will request no extra facility coolant and infrastructure change here. Second one means the solution will have independent rack cooling control system. The solution is under development now, and we plan to have a working L11 system in Q3 this year. The L11 tests will start from Q4 this year. William will contribute the design drawing and the test result to OCP in next year. I would like to share the design factors and the design target we will plan to do. First is about the performance. As we know, cold plate and active rear-door heat exchanger are two key parts in this solution for heat dissipation. So, active rear-door heat exchanger, the mechanical dimension design we will follow and meet OCP door heat exchanger spec. You can check the detailed dimension here. And for the total weight with coolant, it will be under 150 kg. And the current OpenRack v3 power design will support up to 33 or 36 kW per rack. This means we must limit our maximum airflow rate usage. In order to meet 0.17 per watt design target, so airflow usage will be under 3300 CFM and support one fan or one rotor redundancy. As we know, 70% rack power is from the main chip like a CPU, GPU, or ASIC. So for the active rear-door heat exchanger, the cooling capacity design target support up to 33 kilowatts. Next one, we want to talk about the cold plate performance. We did a single cold plate performance test with the 250 watt TTB and using water as a coolant. At 1 LPM scenario, current thermal resistance can touch to 0.036 and the pressure drop is to 4.2 kPa. We also test the cold plate design by a serial design with no quick disconnector because we plan to implement the cold plate module in one-use break cold system. So we can see the pressure drop will go up to 30 kPa at 1 LPM. And why we plan to add the internal quick disconnect between the two cold plates? This is consider another design factor here. This is for the serviceability. In order to make sure the cold plate maintenance will be easy to assembly, we plan to add the internal quick disconnector between the two cold plates and using a soft tube for, as I mentioned, for system assembly and disassembly. Add the extra internal quick disconnect here, it's possible to maintain and disassemble the single cold plate separately, like this photo show. Of course, we also need to modify the chassis design for cold plate pipe routing and make sure we can assemble the cold plate slide up and slide down. For the rack manifold, in order to maintain the service from cold air as current pure usage, so we plan to use the primary self-alignment quick disconnector as the coolant interface between the L10 system and the rack manifold. And for CDU and the rack manifold and the rear door changer, we prefer to use the manual made quick disconnector to simplify the design. And for rack manifold, we prefer to use the two separate manifold to balance the connect force, and we can get more force for quick disconnector sizing to meet different system requirements. As we mentioned before, the solution will have independent cooling control system. So next design factor we want to discuss about the control. We can check here the CDU will own the control to control the fan on the active rear door heat exchanger and the pump speed in the CDU. And for the IT gears, the IT gear will control a system fan by BMC. If set the control, CDU also can monitor all sensors and the status of the CDU and the rear door heat exchanger. And here I want to mention here is about the cooling power assumption. We will design the CDU to monitor except the temperature, also including the power consumption. This is for future to estimate the cooling power consumption. The last one is compatible design. Because the CDU, the design will not only implement in open rack, it also can implement in 19-inch rack. So for CDU, like dimension design, we will design for 4U 19-inch CDU and design extra kit to fit open rack. And for power, we will design to support 48 volts and 12 volts with a power bus bar, and design the possibility to use the external PSU for support 90-inch rack. We will keep optimize the cold plate design for better serviceability. Of course, another is about the coolant leakage. As we know, in liquid cooling solution, coolant leakage is a main concern for user. We'll keep optimize the leakage design for safety. Last one is we will try to expand the CDU's functionality for better control and management. This is all my presentation, and if any idea or suggestion is very welcome. And we also hope more partners join the ACS together, so you can access the below link to get more information about the ACS sub-project. Thank you.
We Win, your best choice for workload optimization and TCO.
Hello? Now is the likely question and answer time. So, any question? Hello? Now it's okay? Hello?
But you're free to answer questions.
I think now the audio should be okay, right? So I can answer the question by the audio, right? Okay, first question is about is the fan wall in the pull or push configuration. So I think the question is about the airflow. So for the air tip, for the design of the active radial changer, the airflow is push out, pulling the airflow from the coil and push out to the high. Question is if I can share about the 250-watt TTP details, I think you can email me. We can share more detailed information to you by mail. And another question is about what percentage of the load are you cooling? About this question, I think currently we estimate 70% of the total rack air power will cooling by the liquid loop, coolant loop. It means the we will assume the main chip
CPU power or like GPU power will be the 70% of the total rack power. So that's that means why I say 70% cooling power will cooling by the coolant loop. And another question is about in the presentation, the cold plate thermal resistance. The thermal resistance is the simple cold plate thermal resistance, which shown in the slide. Here's another question is about, do you have an individual pump in all servers? The question is, I think current in this version, the whole coolant circuit will depend on the pump in the CDU to complete the whole coolant loop. So I think this question should be we will have no individual pump in each server.